So the next part we will see is memory locations and different addresses. So how a memory location is represented and how its addresses are basically represented. So here we will see how the memory of computer is organized, and then in terms of memory, the basic property of memory is like memory consists of many millions of storage cells. So these storage cells are like, it will be storage cells will be like in terms of a bit representation. How many bits of memory is there? If it is of 10 bit, a single bit cell 10 times will be there. Okay. So based on that, you can consider like if 1 MB memory is there, in 1 MB, basically there is 1024 KB kilobyte memory, or you can consider like 1024 into 1024 bits of memory will be there into 1 MB memory location, and that much of bit you can consider once multiplying this, you can get like this much of 1 bit locations will be available into the memory cell. Okay, and memory will be in terms of like storing the data in terms of zeros and one. Okay, so the different storage cells will be there, and each of which cell can store a bit of information having 0 or 1, and these 0 and 1 combination is basically going to represent a data. So usually bits are accessed in groups of fixed size. So these are different bits. So in terms of memories, different memories are there. So set of bits are going to have a pattern basically. So if 1 MB data is there, so we are not going to access 1 bit at a time. What we will be doing is we will be dividing this 1 MB complete data into a fixed size of accessible data. Okay, so we can consider it like 8 bit. Similarly, suppose 8 bit is there. So we will be taking 8 bit at a time, and we will be accessing the data, and we will be processing the data and then storing or whatever we will be doing with respect to that 8 bit combination only. It is a fixed size. So we will be taking a fixed size. So this 8 bit is with respect to like 8085 processor. So in 8085, basically we see the 8 bit processing. So we are going to do the 8 bit arrangement, and with respect to that we are going to operate the system. Similarly, if it is 8086, we are going to take 16 bit at a time. Okay, but this fixed size is generally considered as 8 bit. Okay, here in each group of n bits is referred to as a word of information. So if suppose n bits are there, if we are making a group of n bits, so this fixed size of n bit we can call it as a word. Okay, and n is called the word length. So this is one word, and the number of bits available into this one word is called word length. Okay, so here this n will be considered as the word length, and set of n bits will be considered as one word. So this basically there is much confusion between a word and a bit and a byte. So you should be taking care of it. So word and word length. So what is a word? Okay, so group of n bits is going to be represented as word, and this group of n bits will be decided by the type of architecture we are using or type of processor we are using. So if 8085 is there, so here it is going to operate on 8 bit of data at a time. So this 8085 will be having a one word length of 8 bit. So here in case of 8085, one word will be equals to 8 bits. or 8 bit is equals to 1 byte. So in case of 8085. Similarly, if 8086 is there, so because it is a 16-bit processor, that means it can access 16 bit at a time. So here in case of 8086, one word is equals to 16 bit. 16 bit is considered as 2 byte. So 2 byte of data will be equivalent to 1 word. So based on the type of architecture, we will be defining the a word length or a word. But if 8 bit is there, that is considered as 1 byte. Okay, so 8 bit data is there, it will be considered as 1 byte. But based on the architecture, we will be defining whether it is 1 word or 2 word or 3 word. So in terms of 8085, if 1 word we are saying, that means it will be equals to 8 bits. If in terms of architecture of 8086 processor, we are talking about 1 word, there will be a 16 bit or a 2 byte. Okay. So that you will be getting clear once we see the later points. So in modern computers, we have word length that typically range from 16 to 64. So in modern computers, we are having, suppose what computers we are using is having is of 64-bit computer processors are there. So 64-bit computers means 64-bit the processor is going to access 64-bit of data at a time. Okay, so here one word will be equals to 64 bits, or if it is 64-bit means it will be equals to 8 byte of data. So here in terms of 64-bit processor, one word will be equals to 8 byte, or one word will be equals to 64 bits. So I hope you have got the point. In terms of like 16 bit is there, the word length is there. Okay, 16-bit microprocessor is there, then it will be having a word length of 16 bit. The next point we will see is how the memory locations are given. So this is a memory word is there. If this is the memory location, okay, so this memory, if a memory word is there, so here it is representing n bits, means n bits are there. Okay, so this n bits are there, so it is divided into different blocks. So n bit, and this is one word, so n bit will be one word. So the different words are there. So this is first word, this is second word, similarly this is some ith word, and similarly this will be the last word. So a memory is there, it will be represented in terms of a set or fixed bit number of bits, and if one set of bits are available, this will be considered as one word. Similarly this was another word, similarly this is like ith word. Okay, and this is the last word. Okay, so I hope we have got the point. So accessing the memory to store or retrieve a single item of information, either a word or a byte, requires distinct names or addresses for each location. So here we are going to suppose access first word. So first word is going to have a fixed address. So here suppose if this is n bits are given, suppose in case of 8086 we are having address lines of 20 bits. So if 20 bits are there for address lines, or in case of like 8085 processor, we are having 16 bit of address lines. So each address, so this is one word, each address will be represented by 16 bits. So starting with 0000, this is 4, this is 4, 8, 12, 16. So this is the 16-bit address is there. So starting with, if it is 16-bit address is there, starting with 0000, the last one will be represented by 16 times 1. Okay, so the starting address, starting location of the memory will be given by the 000. In hexadecimal, we can write it as 0000H, because in hexadecimal 4 bits are represented by one single 0, 4 bits will be represented by 0, 4 bits will be represented by 0, 4 bits will be represented by 0. And then to write it like it is a hexadecimal representation, we have to write H at the last. So 000H. Similarly, at the end, we can see like 4 bits representation of 1111 will be equals to F, 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 F. So the last location address will be F, 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 H. It is in hexadecimal. So this is how basically we represent the memory. So in memory, it will be storing n bits of data. One location will be storing n bits of data, and one location will be represented by a set of addresses. So that address will be depending on the address lines. So if suppose two address lines are there, that means if two address lines are there, 2 to the power 2, that will be equals to 4. That means two address lines are there, so it can locate 4 different locations. So first one will be 0001 1011. So based on the two address lines, we are having 4 possible combinations. Similarly, we are having 10 address lines. We can have 2 to the power 10 locations. Similarly, if we are having like 16-bit address lines, we can have 2 to the power 16 means 65536 bits of location or 64 kilobits or kilobits of information. Similarly, for 20 bits of address lines, we can have 2 to the power 20. That means this much of bits or 1024 kilobits or 1 MB of location access, or 1 MB of memory we can access. Okay, so this is the basic representation. So another one we can just see, if the word length of a computer is suppose 32 bit, a single word can store a 32 bits signed number or 4 SCI encoded ASCII encoded characters occupying 8 bits. So here, if any computer is there that is of 32-bit computer is there, that means one word will be representing 32-bit. So this is the 32-bit. Okay, so starting with B0, B1 up to B30 and B31. So this is complete 32-bit. So if it is going to represent a signed number, so the last bit will be representing the sign bit called the sign bit. So sign bit is there. So if B31 is 0, that means the number is positive. If B31 is 1, that means the number is negative. And number value, what number it is going to represent will be given by this location. So whatever the data available from B0 to B30 will be given by the data. This will be the data, and this will be the sign. So in case of 32-bit representation, we can consider this way. Similarly, if it is 32-bit of word is there, 32-bit length of word is there, and it is going to occupy by ASCII characters. So one ASCII character is of 8-bit. So it can store up to 4 characters. Okay, 4 ASCII characters. So this next we will see into the next class. Okay, so the next point we will be seeing into the next class, or just yes, just see that there are only 2 slides are there further. So here byte addressability basically is here. Byte addressability in the sense like there are three basic information quantities to deal with is bit, byte, and a word. So when we are going to have a data access, we can access it in terms of bits or in terms of bytes or in terms of word. A byte is always of 8 bit, but the word length typically ranges from 16 to 64 bit. So byte length is fixed, but word length is not fixed. So it is impractical to assign distinct addresses to individual bit locations in the memory. So we cannot have different addresses for different bit location. So that's why the most practical assignment is to have successive addresses to refer successive byte locations into the memory. That means so if this is the memory location we have seen, it's not like we randomly assign here some address and here some another address next. This is not a random assignment. There is a successive assignment in the sense like if we are starting with the 0000, then the next one will be 0001. Suppose it is a 4-bit representation is there. So 0000, so it will be 0001. The next memory location will be represented by 0010. Similarly, the next one is 0011. So that is the representation of memory location. Okay, so it will be in terms of successive addresses. So if we know the first one, what will be the next address? We know like it will be one increment to the previous one. This is the assignment used in most of the modern computers. So successive assignment of addresses is basically used. The term byte addressable memory is used for this assignment. So byte addressable is used for this assignment basically. Byte addressable means one byte will be addressed by one memory location. So byte locations have addresses like 0, 1, 2, and 1. So 0, 1, 2 means one byte. Suppose this is one byte of data. One location is representing one byte of data, and this is given by 0000. Next byte of information will be given by 0001. Okay, similarly, so here it will be represented by location 0, then 1, 2, and so on. So therefore, if we consider like thus, if a word length of a machine is 32-bit, if a machine is there, it is having a 32-bit word length. Successive words are located at addresses 0, 4, 8, and so on, with each word consisting of 4 bytes. So if a 32-bit memory processor is there, basically, it is going to access the data. If we want to access the memory location, suppose 32-bit is there. In 32-bit, we are having 4 byte. Is 32-bit word length is there. So one word is equals to 4 byte. So 32-bit type of machine is there. It will be having 32-bit as a one word. It will be equals to 4 byte. So 1 byte is represented by this location. This location is 1 byte. Next, if this one is now combined, this is 2 byte. This is 3 byte. Now from here to here, it is 3 byte. Now here, this is 4 byte information. This is 4 byte. So this 4 byte will be considered as the one word. So if 32-bit type of machine is there, 4 bytes will be considered as one word. So the first word location will be from 0. The second word location will be from, this is suppose 1 byte, another byte, this is another byte, and this is another byte. So here, this is the second word. This is the first word. So first word is represented by 4 different bytes, and 1 byte will be represented by location 0000. In decimal, we are just writing if it is 0000. In decimal, it will be 0. Then in decimal, it will be 1. This will be 2. This will be 3. This will be 4, 5, 6, 7, 8, and so on. So 1, 0 location in decimal is represented by representing 1 byte. Similarly, 2 is going to represent another byte. 3 up to here, they are going to represent another bytes. But 4 byte is consist of one word. So for word, this 4 bytes is constituting one word. So the one for one word, the location will be 0. For another word, second word, the location will be starting with 4. So 4, and then similarly, the for third one, it will be starting with 8. So this is what is written. So if a 32-bit machine is there, then its successive word locations will be from 0 to 4 to 8, and then after add, we will be getting 12. So in terms of 12, this is in terms of decimal we are writing, okay? 12 and 16 and so on. So each word will be consisting of 4 bytes. So we have seen like words, what is a word and what is a byte. In 1 byte, we know it as 8 bits, and in a word, there is no fixed number of bytes. Basically, word will always be defined in terms of bytes itself. But depending on the processor that we are using, a word will be different for different processors. So we have seen that. So in that also, if in this case here we have seen if it is like a machine is there or a processor is there that is of 32-bit, that means its word length is of 32-bit, then it will be constituting of 4 different bytes. So suppose this is a 1 byte, this is a 1 byte location from here to here. So similar to this, 4 different locations will be constituting one word. Okay. So one word location will be starting with the 0. The next word location will be starting with the 4. Okay. So once we are going to specify a word, different bytes will be used to represent the word complete word size. So this is a word in that 4 different bytes are there. So this is 1 byte, this is 1 byte, this is 1 byte, this is 1 byte, and this complete is a word. Okay. So in this also, we will be basically saying 2 different byte addresses, like how we can define a word by 2 different assignment methods. So one of the assignment method is called big Endian. Second one is little Endian. So a word can be represented by here. A word is of 32-bit. So this word will be of 4 bytes. It will be constituting 4 bytes. So these 4 bytes, how it should be arranged is basically represented by 2 different methods. So one is big Endian and another one is little Endian. So we will see that. So here you can just see here from the figure. So this is the representation of this is one word. So this is word address. So this is 0. That means it is talking about the first word. If it is 4, that means it is talking about the second word. Similarly, whatever 2 to the power is there, if kth, if we are having like k bits into a byte, basically if we consider here, right? So with respect to that, we can say like here we are going to have 2 to the power k minus 4. So whatever 2 to the power 4, 2 to the power k minus 4 is there. So if we talk about this representation, if we are having k equals to 0 is there, or in terms of that here 2 to the power, because it is of 32-bit representation is there. So here we will be considering like 2 to the power 2. If we are considering, it will be 4 minus 4, it is 0. Okay, so this basically represents the general representation of this one. So starting with 2 to the power 4, we will be starting like at least 2 bits are available, or 2 we are going to represent in terms of k. So if a big Indian assignment representation is there. In that case, so this is byte 0, byte 1, byte 2, byte 3. That means one word is going to constitute 4 different bytes, and these 4 different bytes are represented by the location. Like the first byte is considered from the MSB. So if any data is there, if suppose we are written 0010, so here this one, or you can say the rightmost, is called LSB, and the leftmost bit is called MSB. So I hope everyone knows that. So in case of word representation, if a word is there that is of 4 byte part, in that case, if we are going to represent first or 0th byte with the MSB and the highest byte to the LSB, then that representation will be called as the big Indian assignment. In the opposite, you can just see here it is also the same. We are going to represent one word. One word is being represented by 4 different bytes, and here the 4 different bytes are there, like the 0th byte that is there, that is going to represent the LSB. The first byte is going to represent, okay, the second byte of the word, and finally the highest byte is going to represent the MSB. So this type of representation is called Little India. So there are basically 2 different type of representations are there.
Excuse
So
me,
you can
sir.
just, yes.
So will there always be 4 bytes in a single word, or so it can
No,
have
no,
more
no,
than 4?
no. So we have just taken an example of a word that is of 32 bits. Okay. So if we are going to use like 64-bit processor, then the word length will be 64. So if 64 are there, that means in one word, instead of 4, there will be 8 bytes will be there. So if just take the example, okay, so suppose if 64 bit word length is there, then one word will be constituting 64 bit. Okay, suppose this is the first word. The second word will be represented at what location? At what
So
location it will be?
16. So
No,
16 or
not.
8.
It will be 8. Why? Because in one word we are going to have, because it is of 16 bit, so 64 bit, so we need to have, we will be dividing it by 8, because one byte is going to have 8 bits. Okay, 8 bit is 1 byte, so we will be dividing, that means 8 is coming out, so there will be 8 bytes into 64 bit word length, so there will be 8 different. Okay, so if we are going to represent in terms of big Indian assignment, then it will be starting with like the MSB will be represented by the 0th byte. So here 0 will be there, byte 0, byte 1, byte 2, 3, 4, 5, 6, 7, and 8. Sorry. So once it is going to 1, 2, 3, 4, 5, 6, 7, 8. We have given extra. It will be up to 7 only. Okay. So this is the first word. In case of 64-bit word length is there. If word length is of 64 bit, then the first word will be represented by 0 location. This will be the address. At that address, there will be 8 different bytes. And in that 8 different bytes, if the 0th byte is going to represent the MSB and the highest byte is going to represent the LSB, then it will be considered as big Indian representation. Similarly, if we want to represent in terms of little Indian in, assignment, then similar we can write, we will be changing the byte representation. So here 0th byte will be there, and here the highest byte, that is 7, will be there. If we are going to represent the next word, so this was the first word, suppose this is the second word. If this is the second word, to represent the second word, what we need to do is, again, because this is the different words, so up to 7, so now the next byte will be 8, 9, 10, because in case of a memory, if we can see, a memory is like that. In that memory, always we will be writing like one block of this memory will be of 1 byte. Okay, and it will be having an address. Similarly, another address, and here 1 byte of data will be stored. Similarly, 1 byte of data will be stored at this. Okay, so in a memory, different blocks will be like that. But we know in case of 64-bit word length, we need to have 8 bytes. So this is the first byte, we will be representing 0. This is the second byte, third byte, because starting with 0, 1, this will be 2, 3, 4, 5, 6, 7, like that. These are the different bytes. Okay, so these bytes are written here. So instead of representing a memory like that, we are going to represent the memory in terms of words. So generally the memory will be represented by this. Okay, this will be the size of memory. In that, different blocks will be of 1 byte. Okay, and it will be having an address. But once we are going to represent in terms of words, so 0th location will be going to represent 1 word, and in 1 word there will be 8 bytes. So 8 byte means starting with 0 up to 7. So up to here, this location will be considered as 1 word in case of 64-bit word length. Okay, the next word length will be starting with, like, instead of 7, after 7 it will be like here 8, 9, 10. So in the next word, the minimum location or minimum value of the byte that is going to represent is here 8, 9, 10, 11, 12, 13, 14, 15, and so on. So that means in the word also, like in a word, different bytes are there, and different bytes are going to represent a word. So at what location we are going to represent the byte, that will be indicating whether it is big Indian or little Indian. So if the smaller bytes are going to represent the MSB, then it will be considered as the big Indian. So here again, in the second word also, 8 is smaller and it is going to represent the MSB of that word. Then the 15 is the larger one in the byte, and it is going to represent the LSB side. So this is LSB side and this is MSB side. Okay, its opposite will be the little Indian. So I hope it is clear.
Yes, sir.
Okay, yeah, thank you. Yeah, so we will just go through the theory part also, like what it is saying. So here, big Indian used when lower byte address. So lower byte addresses are used for the more significant byte or leftmost byte of the word. So here, lower byte addresses. So here, this is the byte. This is the 0th byte, 1 byte, second byte, third. So this is basically the address of a byte. So in this case, like if this is the byte, its address will be, so we'll have the location. Just we will see the address, how the addresses can be defined here. So basically, if suppose the address is of, suppose in 8085, address are 16-bit addresses are there. 8085 16-bit address lines are there. That means one address of a memory location will be represented by 16 bits. So in 16-bit we can represent in terms of hexadecimal. So there will be four digits. Okay. So starting with 0000 hexadecimal to 1 or F hexadecimal. This will be the address of all possible address by using 16 address lines or 16-bit address line or 16 address lines we can consider. Okay, so if in this case also suppose it is of 16-bit address line, so starting with 0000, so in decimal its representation will be 0. For the second byte, what we will be doing is we are going to increase 1, so 000, and this one will be 1. Okay, so this is 1. Similarly it will be 2. Okay, so 000 in terms of like 2. So in this we are going to increase continuously. So we are going to increase in terms of like so this is 1 in hexadecimal. Okay, so similarly 0002 in hexadecimal, 0003 in hexadecimal. These are the hexadecimal numbers. Okay, so this we are going to represent is here. So this 0 is nothing but a hexadecimal number. This is 1 is another hexadecimal number. Okay, so similarly instead of here 10 11 12 13 14 15 we have written, so instead of that we need to write in hexadecimal. So in hexadecimal it will be 9. After 9 it will be A, B, C, D, E and F, and after that again the next address whatever it will be there, that will be 10. Okay, then 11. Okay, so this is how hexadecimal representation is there. So basically it is going to say like the lower byte address. So this is the lower byte address or this is the lower one. So if in one word there are 8 bytes, so out of these 8 bytes there will be each byte will be having a address. So the byte that is having the lower address will be going to represent the leftmost byte of the word. So this is the word here, this will be the MSB, this will be the MSB, and this is LSB. So the leftmost byte of the word will be represented by the lower byte address. So lower byte address is 0. Similarly, in the next definition, little endian is used when lower byte address. So lower byte address, this one is the lower byte address, are used for the less significant byte or the rightmost byte of the word. So this is a word, this is the LSB, this is the MSB, or LSB is least significant bit or byte. Okay, so in case of word it will be least significant byte. Okay, so this is least significant byte is there, or the least significant is on the right side. So this is right side byte. So right side byte will be represented by lower byte address. So lower byte address of the lower byte address of a byte. So and high MSB will be represented by the higher byte address. So in case of like providing the addresses to a memory location, different trends are followed. So in that, in between, there are two different basically used, big endian and little endian. It can be any of that we can use in further analysis. Okay. The next one is word alignment. So always the word alignment we have seen. So starting with 0, it is 4, and then it will be 8. Similar to that, it will be instead of 12, we will be writing in terms of like hexadecimal. So 12 will be C. Okay. So like that, it will be represented. So different word alignments are there. So these word alignments is in a regular manner. Like it's not like here 0 and then here we are writing 8, or then here we are writing C, and then there is an order in which we are going to represent. Okay. So this order must be followed. This order, if we are going to represent these words, in an orderly manner, then it will be easy for the user itself to have the clear understanding. Okay, so in case of a 32-bit word length, natural word boundaries occurs at 0, 4, 8 and so on. So we have seen already. So word locations have aligned addresses. So word locations are having aligned addresses. They are having in an ordered addresses. If they begin at a byte address, that is a multiple of number of bytes in a word. Okay, so if it begin with a byte address, it will be always in terms of the different multiple of byte address itself. And there is no fundamental reason why words cannot begin at an arbitrary byte address. So it is not like there is no region like we cannot use the random addresses. We can use the random addresses also, but if we are going to use an aligned address of a word, it will be like an easy way for the user itself. So if we are not going to use an aligned words, aligned bytes into the words, so in that case the word are said to be unaligned, have unaligned addresses. But the most common case is to use aligned addresses, which makes accessing of memory operand more efficient. So if we want to access the data, it will be more efficient if we are arranging the words into an order. Next is accessing numbers and characters. So basically, once a processor is going to access any data from the memory location, there are different techniques we generally use to access this data. So that techniques are different ways in which we will be analyzing the data. Accessing the address data from the memory is called addressing modes. So we will see that later into this class. So here a number usually occupies one word and can be accessed in the memory by specifying its word address. So any data is there or any number is there, so it will be occupying a word. So a one word is there, so one data is, suppose 10 is written into 10 is the data, it is the data, it will be stored. Suppose this is a word and suppose word length is of 32, so then 10 will be represented on in terms of 32-bit representation. Okay, so starting with 000, at the last it will be like 1010, because 1010 is going to give the 10, and here it will be 000, so it will equivalent to 10 itself. So here at this word length we are going to store the data like that in terms of one word. Okay, similarly individual characters can be accessed by their byte addresses. So this is the data that is stored at that word location, and this word location will be having an address. So once we want to access the data from this or from this or suppose we want to access the data of 10, then we need to access the data by its address. Whatever its address is there, we will be using that address to access the data. And that it's not like once we are having that address, we will be directly getting. So what internally will be taking place is with the help of buses. So we have different buses inside the architecture of the CPU basically. So these buses are like address bus, data bus, and control bus. So once we want to access that address, we will be using address bus. If we want to have data from a particular location, we need to access the data with respect to its address. Okay, so if a character is also there into that location, so character will be also in terms of access in terms of the bytes only, or the address, whatever the address is there, address, different address bytes will be there. So if it is 16 bit address is there, that means it is of 2 bytes, 2 byte address is there, so we can access from there. So for programming convenience, it is useful to have different ways of specifying addresses in the program instructions. So accessing a data with the help of its address can be done in different ways. So one instruction is there, suppose add a comma, and then we have given the address directly. So here we are directly providing the address. Sometimes we will be placing this address into a register. We have placed this address inside this register and we are accessing this register. Sometimes we will be directly giving the data. Okay. So there are different ways through which we can access the data from its location. So these different ways of specifying addresses in a program instruction is called addressing modes. So in the next class onwards, we will be going with the different types of instructions and different formats, like what different formats architecture can support while going with different type of instructions, and also we will see the different addressing modes. Okay, so thank you.